what happens if we just kind of figure out what's going on in between these regions? So we're just going to make up something. We just know that we're going to get more information. We're going to get a more detailed graph in here. Okay, so what's going to happen if we get a more detailed graph? So, for example, I can say that, it was that in between, it just happened to hit that point. Okay, so I'm going to say that is 32 meters per second at 1 second. So what we're going to do is we're just going to add more detail to this graph, and we're going to see what happens as we add more detail. Okay, as we add more detail to this graph, okay, so it's going to be like this. Okay, and maybe here it's going to speed right up to 39 really quickly and then kind of level off. Now you're going to choose values different than mine. You can't choose my values. You have to choose something different. You could choose an average if you want. Okay, you can be creative, but we just have to know that it's always increasing. So in this case here, it's going to go to 41. So it's going to go really slow and then go up fast. Okay, and this one's going to be right in the middle. Let's just say this is average. Let's say that's 51. Okay. And again, you can't choose, you just need to choose other values different than mine. You can choose whatever values you want, but it has to be different than mine. Okay? And you got to do your own calculations here. Okay, so based on my values, I'm going to do my calculations. Your calculations should be different. Okay, so if I use my lower Riemann sum, I'm going to use a 30 to find my first interval, 32, 36, 30. These are my left-hand Riemann sums, and these are giving me lower Riemann sum values. Okay, so we're not going to use that one. And then I'm going to use a right-hand Riemann sum, so I'm not going to use that right edge. I'm going to use this left, so I'm not going to use the left edge here. I'm going to use a right edge, so I'm going to use 32 as my first area. These are all just going to be the same because they're 1 second intervals now. Okay, so we want to then figure out, now that we have more detailed information because we have thinner intervals, what's going to happen to our estimates? Okay, now yours should be different than mine. Your totals should be different than mine. Okay, but we're going to see something happen here. So we're going to have our 1 second interval, my low estimate here. If I add this up, well, I should have a calculator, but in fact, I'm going to just quickly grab a calculator if I can find one handy here. Okay, so I'm going to add up these values and find my low estimate and my high estimate. Okay, so I've got 30 plus 32 plus 36 plus 39 plus 40. And please do this for your own. Okay, you're going to have different values than mine. Okay, so mine ended up being 429 as my low estimate meters of displacement. And for my high estimate, I'm going to have, if I add that all up, I'm going to end up with 459 meters of displacement. And so think about what's going to happen. If I have more detail to the graph, I'm going to be able to more closely estimate the actual displacement here. That's because I've just kind of made these intervals smaller. And as I make these intervals smaller, I'm getting more detail, which should give me a better estimate. And so when I look at that's now my low and high, and my margin of error should decrease. Okay, so what's going to happen is I'm going to end up with a margin of error that looks like this: 459 minus 429 meters. And I'm going to get a margin of error, okay, which we call margin of error, is going to be equal to 30 meters. Okay. Now, what might be surprising is even if you chose different numbers, you should get the same margin of error. And you can, if you kind of look closely at the data, you can probably figure out why. And I'll leave that up to you. But the more important issue here is that as we add more detail to the graph or make our intervals smaller, we are going to get more information. We are going to get a more accurate accurate idea of what's going on, and we're going to get a lower margin of error. In this case, it's exactly half because we added twice the detail. So this is the idea of Riemann sums, okay? And this idea of Riemann sums are the two main ideas here. First of all, there's actually a few main ideas. Velocity times time gives us distance or displacement. So the area underneath a velocity graph is the displacement. Okay, some of you already knew this. We're going to use rectangular areas to calculate these or estimate these areas. Even though it might be under a curve, we're going to use these rectangular areas, which we call Riemann sums. And there's left-hand Riemann sums and right-hand Riemann sums. And what we did, because there was this issue of strictly increasing, one Riemann sum is going to always be the lower estimate, and the other one would be the higher. It could be strictly decreasing as well, then the opposite would occur. So this issue of when it's strictly decreasing, we can make these kind of assumptions. But otherwise, we're mainly just looking at left-hand and right-hand Riemann sums. Typically in AP Calculus, we use left-hand Riemann sums, although sometimes we use both, and then we're going to use other shapes, another shape called trapezoid, and a little bit later. Okay, so we're just going to practice calculating Riemann sums. That's the main idea. So if I have my velocity time graph here, okay, let's draw this graph in first. Okay, so I'm going to have 15 meters per second. Okay, I'm going to have 25 at 2 seconds, 28, 30, 35, 45, somewhere around here. Okay, and then I'm going to do my lower Riemann sum. Okay, I'm going to use that area here, so it's going to be 30, this area here, this area here, this area here, and that area here. So that's going to be 30, 50, 56, 60, 70, 90, and my left hand, oops, I'm not going to use 90 there because I'm not going to use that last bit. So 130, 186, 136, sorry, 236, 266 meters. Okay, that's what I'm getting for my left-hand Riemann sum. Okay, and then for the upper Riemann sum, I'm actually going to do it just on the same graph here. Okay, for my upper Riemann sum, it's going to be using this bar, this bar, this bar, this bar, this bar. Okay, so we're just going to be adding on that. So these are all going to be the same. And here I'm going to end up with, looks like a distance of 316 meters. I'm just going to double check here, 150, 220, plus 160, 220, 226, 326. Okay. So those are my left hand and right hand Riemann sums, and they represent, in this particular case, if we don't actually, this one hasn't told if it's strictly increasing or not, so we don't know what's going on here. So we can't actually say that the left hand Riemann sum is the lower bound and that one's the upper bound, right? Because it could look like that. The graph, you know, it could have gone down like that. We don't know. Okay, so we don't know what's happening in between. So our left hand Riemann sum, okay, is going to be 266, and that happens to be, well, we'll call that a lower Riemann sum anyways, because we'll say that that one is our strictly increasing region and graphs, and then we can make that statement. and we have our right-hand Riemann sum here. Okay, and this issue of lower and upper really is actually secondary to this issue of left and right.